There's a boundary in space where the rules of reality break down, a place where time itself bends, stretches, and eventually stops. Cross that line and there's no return, no second chance, no escape. You would fall towards something that doesn't just destroy matter, it erases the very concept of existence as we understand it. This is what happens when you fall into a black hole. For most of human history, black holes were nothing more than mathematical curiosities. Einstein's equations predicted them, but even he doubted they could be real. How could something exist that devours light itself? How could gravity become so powerful that it tears the fabric of space-time? Yet, we now know they're not just real, they're everywhere. Millions of them drift through our galaxy alone, invisible predators lurking in the cosmic dark. And if you were to fall into one, your final moments would be unlike anything else in the known universe. Let's begin at a distance. You're approaching a stellar mass black hole, perhaps 10 times the mass of our sun. From here, it doesn't look like much. In fact, you can't see it at all. Black holes don't emit light. They're defined by what they take, not what they give. But you'd notice something else. A disk of superheated gas and debris spiraling around an absence, glowing with impossible brightness. This is the accretion disk, matter being ripped apart and accelerated to nearly the speed of light before it vanishes forever. The radiation here would kill you instantly, but let's imagine you have protection. Let's imagine you can survive long enough to see what comes next. As you drift closer, something strange begins to happen. Time itself starts to behave differently. If someone were watching you from a safe distance, they would see you moving slower and slower. Your gestures would become sluggish. Your signals would stretch out, redshifted into longer and longer wavelengths. To them, you would appear to freeze at the edge of the black hole, suspended forever in your final moment. But that's not what you would experience. From your perspective, time continues normally. You keep falling. This is relativity at its most extreme. Time is no longer universal. Your clock and theirs have become fundamentally disconnected. You're approaching the event horizon now. This is the point of no return, the boundary where escape velocity exceeds the speed of light. It's not a physical surface. There's no wall, no barrier you can touch. It's simply the distance from which nothing, not even light, can climb back out of the gravitational well. Once you cross it, your future contains only one destination, the singularity at the center. Every possible path through space-time now leads inward. Moving away from the center becomes as impossible as traveling backward in time. But before you reach that point, something horrifying begins. It starts subtly, a slight stretching sensation in your body. Your feet, closer to the black hole than your head, experience stronger gravity. This difference creates a tidal force pulling your feet down harder than your head. At first, it's gentle, then it becomes uncomfortable, then agonizing. This is spaghettification, and it's exactly as terrible as it sounds. Your body begins to stretch like taffy. Your bones elongate. Your cells pull apart. The gravitational gradient becomes so steep that even the molecular bonds holding you together start to fail. For a stellar mass black hole, this happens before you even cross the event horizon. You would be torn apart while still technically able to escape, if only you weren't already being shredded into a stream of atoms. But here's something strange. If the black hole were supermassive, millions or billions of times the mass of the sun, the event horizon would be so far from the center that tidal forces at the boundary would be gentle. You could cross it intact, still alive, still conscious. You would pass through the point of no return without even noticing. Imagine that. Imagine crossing the event horizon of a supermassive black hole and continuing to fall, surrounded by darkness, knowing that you've just severed every connection to the universe you came from. Every photon trying to escape with you curves back inward. Every signal you might send would never reach home. You are now causally disconnected from the rest of reality. To the outside universe, you effectively no longer exist. What would you see? The view would be impossible to describe. Light from the universe behind you would be compressed and blue shifted into a bright ring surrounding the darkness ahead. The entire cosmos would appear to squeeze into a shrinking circle above you. Time outside would appear to accelerate dramatically. You might see the distant future of the universe play out and fast forward, stars dying, galaxies colliding, all compressed into your final seconds. Meanwhile, below you, there would be nothing but infinite darkness. The singularity doesn't emit light, it doesn't reflect it, it simply is. And here's where physics breaks down completely. As you fall closer to the singularity, tidal forces grow without limit. Even in a supermassive black hole, eventually, you reach a point where the stretching becomes infinite. Space itself is curved so severely that our equations stop making sense. The singularity is predicted to be a point of infinite density, where all the black hole's math is compressed into zero volume. But what does that actually mean? We don't know. General relativity, our best theory of gravity, cannot describe what happens at the singularity. Quantum mechanics, our best theory of the very small, offers no clear answers either. These two pillars of modern physics contradict each other at this exact point.
Some theories suggest you wouldn't reach a singularity at all. Perhaps you'd encounter a quantum structure we can't yet understand. Perhaps space-time itself becomes foam-like and chaotic at these scales. Some speculative ideas even propose that black holes might be tunnels to other regions of space-time, though there's no evidence for this and you almost certainly wouldn't survive to find out. What we can say with confidence is this: whatever happens, it's the most extreme physical process in the universe. Nothing, no supernova, no collision of neutron stars, no explosion at the birth of the cosmos creates conditions more violent than those at the heart of a black hole. And then, nothing. You would simply cease to be in a way more absolute than any other death imaginable. Not just your body, but your information, your history, the specific arrangement of atoms that made you unique, all of it consumed by an object that reveals nothing about what it has devoured. But here's the deepest mystery. According to quantum mechanics, information cannot be destroyed. It can be scrambled, hidden, transformed, but never truly erased. Black holes seem to violate this principle. They appear to delete information from the universe permanently. Stephen Hawking spent decades wrestling with this paradox. He eventually proposed that black holes do emit radiation, now called Hawking radiation, and slowly evaporate over immense timescales. Perhaps the information isn't destroyed after all. Perhaps it's encoded in that radiation in ways we don't yet understand. Or perhaps the paradox reveals a flaw in our understanding of reality at its most fundamental level. Black holes are more than cosmic predators. They're laboratories testing the limits of physics, the boundaries between the very large and the very small, the places where our knowledge simply ends. Every black hole is a question mark printed on the universe, asking us, do you really understand how reality works? And here's what makes this genuinely unsettling. We live in a universe that permits such things to exist. A universe where gravity can become so extreme that it creates these wounds in space-time, where matter can be compressed so thoroughly that it disappears from causality itself. We orbit a star that will never become a black hole, circling safely in a galaxy where supermassive black holes lurk at the centers of nearly every large galaxy, including our own. 4 million times the mass of the sun, sitting 26,000 light-years away, silent and patient. We will never fall into one. The distances are too vast, the timescales too long, but black holes will outlast everything. Long after the last stars burn out, long after galaxies drift apart into the infinite dark, black holes will remain. And eventually, even they will evaporate, returning their stolen energy to the void. They are both ends and beginnings, destroyers and creators of the most fundamental kind. To fall into one would be to experience the universe at its most honest. No mercy, no meaning, just the raw mathematics of curved space-time playing out to their inevitable conclusion. It would be the loneliest death imaginable and the most absolute. A reminder that for all our science and understanding, there are still places where knowledge ends and only mystery remains.